Hello friends, today we will study quick sort. Quick sort is a sorting technique which applies the strategy of divide and conquer. Divide and conquer strategy will help us using and implementing the quick sort very easily. Now what is quick sort? The quick sort uses divide and conquer while not using the additional storage space. This is one major advantage of quick sort, that is, it does not utilize a special storage space. A quick sort first selects a value which is called as the pivot value. The role of the pivot value is to assist to split the list. Now why is it needed to have a pivot value to sort a particular list? We will see that as we go further and study the quick sort algorithm. The actual position where the pivot value belongs in the final sorted list, commonly called the split point, will be used to divide the list for the subsequent calls to the quick sort. Now this is a very technical definition of how a pivot element and why is it needed. Pivot element is any element which is chosen by the user. It can be either the first element or the last element or any element in the list which the user wants to choose as the pivot element. Now the importance of the pivot element is, after I implement the comparisons, after the first iteration, wherever the pivot value will be stored or wherever is the position of the pivot value, that is the split point of my array. And at that split point, my array and the list will be in such a manner that the values on the left hand side of my pivot will be less and the values on the right hand side of my pivot will be more than the pivot element. Now select a pivot, that is the partitioning element. Here we are taking it as the first element of my list. We are assuming that the first element of my list is the pivot element. Rearrange the list so that all the elements in the first S positions are smaller than or equal to the pivot, and all the elements in the remaining n minus S positions are larger than or equal to the pivot of the list. Now here is a simple example or the simple array definition, that if I have a list at a point where I am splitting it into two parts, that is A of I is less than equal to P, where P is my pivot element, and on my right hand side I have A of I, that is all the elements of my list are greater than or equal to the pivot value. Now exchange the pivot with the last element in the first, that is less than equal to subarray. The pivot is now at its final position, that is after the first iteration my pivot reaches its fixed position. So one element in my array is got its final position, and that is known as the split point, and all the elements to the left and right needs to be sorted in the similar manner with the recursive algorithm of quick sort. And after that we sort the two subarrays recursively. Now what is a partition algorithm? How does the partitioning algorithm works? If P is less than R, that is the pivot element is less than the value over there, then Q, that is we call, and we partition A, P and R. That is, I partition the array with the pivot element and the value R. and recursive call to the quick sort function is continuously given by passing A, P and Q. Q is nothing but the new array which will be created, or the new value which will be created. Now recursive sort to the quick sort is given when I have a second split of my array, that is A is Q plus R and the final value of R. So as I see, once my pivot element has got its fixed position, I have two arrays on the left hand side and on the right hand side, and I then give a recursive call to my quicksort function. Now how does the partitioning algorithm works? Partitioning, I have passed on the value of array A, pivot element and the size of my array. X is A of P. What is that? Whatever is the value of A of P is stored in the variable X. I gets the value of P minus 1. J gets the value of R plus 1. While the condition is true, then what do? I keep on repeating, that is, I keep on moving J minus 1 to the value of J till A of J is less than equal to X. And then what happens? I keep on repeating, that is, I keep on incrementing the value of I till I reach a position where the exchange is no longer possible. That is, until A of I becomes greater than or equal to X. And if I is less than J, what is I and J? That is, the initial value and the final size of my array is, if the initial value is larger than the final size of the array, then what do? Then I start exchanging. If it is more, then I need to exchange the values of A of I and A of J. How this particular partitioning algorithm works, we will see it pictorially. Or if this particular exchange does not happen, then what do? I return the value of J. Now how the particular code is written, let's go by that. For the partition algorithm, I pass the address of my array. Quicksort will be implemented using pointers, so I pass the address location of my array A. I get the low value and the high value. Low value is nothing but the initial value of my array size, that is 0, and high is the last value. So when I pass A, P and R, that is my initial array A, low gets it the value of P and high comes from the value of R. I declare two variables, that is left and right, and then I say void pivot item. Now what is a void pivot item? It just gets the first value of my array, that is A of low. Low is the first element of my array, so that goes to the pivot item. Now pivot is equal to left is equal to low, so that I declare it as left also. So my left also gets the same thing. Right is equal to high, so the last element of my list is passed on to the variable right. Now let us see how the code for the quicksort actually works. That is, after the partitioning, how the quicksort uses the pivot element to put the data at its proper position. While we have to move from left where my item is less than pivot, so my condition is while A of left, that is the data at the left position, is less than or equal to pivot, then I do left plus plus, that is I compare the data at a position of left with the value of the pivot element. So as you see the list below, what we see, 54 is the pivot element, the data at the left is 26 and the data at the right is 20. So the value of A of left is less than equal to pivot. So there is no exchange of data between the pivot and the left. So what do we do next? We then move to the element on the next, that is left is incremented by 1. So when left is incremented by 1, what happens? My left reaches 93. my left reaches 93 and then we have to compare. While A of right is greater than pivot, then we do right minus minus. And if the value of left is less than right, then we swap the two values of left and right. This is a small procedure function for which the quick sort works. We will see in the example how the value of quick sort in which the pivot element gets its final position. And when the right is at the final position for the pivot, what we do, A of low is equal to right and A of right is equal to pivot element. So here we return the value of right to the function from where the partition was called. That is, once the value of the partition is fixed, that is, the value of the partition element is fixed. Now here if you see 26 is less than pivot, so we will reach at 93 and then we will compare 93 with the pivot and so on and so forth. It will continue comparing till my pivot reaches its final position. So now what do? We see an example. Let's take the same list that we have taken in the code. That is, 54 is my pivot element, 26 is the element at left and 20 is the element at right. So what happens? 26 is less than 54, that's the pivot element, and 26 is less, so nothing we do, because in the partitioning we have to place 54 at such a location that on the left hand side you have all the elements whose values are less than 54 and on the right we have all the elements whose values are greater than 54. So my list remains the same. What we do? As we said in the code, we do left plus plus. So as we do left plus plus, my left comes at a position where the value stored is 93. Now we compare. 93 is greater than 54, which is the pivot element. So we do not do anything and we move to the location of right. So my left remains unchanged and I move to right. Now I compare the value of right with the pivot element. 20 is less than 54, that's the pivot element. So what we do? We exchange the values of left and right, that is, we swap the values of left and right in such a way that 93 goes to the position where 20 was stored and 20 comes to the position where 93 was stored. That is, now my left becomes 20 and my right becomes 93 and we do right minus minus. Now again, in the previous list, as left was at 20, now my left gets incremented by 1. So my left is now at 18 and my right is now at 56. Again I compare. 18 is less than 54, so there is no exchange. As there is no exchange, as my code says, we increment the value of left by 1. So what happens? My left gets incremented and reaches to the position where 78 is stored. So as we see, 78, when I compare, it is greater than 54, so I stop over there, and once I stop, then I again compare and move to the location of 56, that is the right element, and now I have to compare whether my 56 is greater than the pivot element or less than the pivot element. I observe that 56 is greater than the pivot element, so there is no exchange that will happen, but you will have a confusion that it is less than 78, but it has to remain on the right hand side as the value of 56 is greater than 54. So we do right minus minus. When I do right minus minus, my right has come to the position of 41. So what do? We again compare 41 with 54. 41 is less than 54, so we exchange the values of left and right. here we have to observe and always be careful that we do not exchange the value with the pivot element, but we exchange the values with the right and the left index variable. So here we will be exchanging the two values. So 41 comes to the location of 78 and 78 goes to the location of 41. This is how it happens when I swap the two values and pivot remains as the first element of the list. Now what do? I again move left plus plus. When I do left plus plus, my left becomes 33. And now left is also incremented by 1 and right is at a location of 78. Here if you see, 78 is greater than 41, and when I say 78 is greater than 41, I exchange the two values, that is what we have just observed. And then what we do, 33 and 78, as we reach to 33 and 78, at this position 33 is less than 54 and 78 is greater than 54. Here the value of left and right cross each other, and when the values of left and right cross each other, that is I increment left plus plus, it reaches 78. At this instant we get that as a partitioning point of my quick sort. So that is the place where my left and right interchange and exchange each other. That is the value, or that is the place where my pivot value has to be stored. So here we exchange the value of left with the pivot. So we observe here that 54 moves to the location of 33 and 33 moves to the location of 54. So here when we exchange the same values, we get this and pivot gets placed at its final position. Now, so at this position, when my pivot is at 54, we have the left margin and the right margin, that is the left part of my sort and the right side of my sort. So the left side has the values all less than 54 and right side has the value all greater than 54. As we've seen that quick sort has allowed, now the pivot element has reached to a position of 54. On the left side is all elements less than the value, on the right side are all elements greater than the value. Now this is an application as we started with a divide and conquer strategy. So what happens now? If we have to now sort the elements on the left hand side, how do we do it again? So what happens next is 54 has got its position fixed. So now we have to apply the same procedure to the left side of the unsorted list and then on the right side of the unsorted list. So we do again in a recursive manner. We start taking 33 as the pivot element for the list. So the list now is 33, 26, 20, 18 and 41. So here we will recursively apply the quicksort algorithm that we have applied for the first pivot element 54. So here in the left side of the list, if we take 33 as the pivot element, and in that case 26 will be left and 41 will be the right element in the list. So we start comparing again, and when we start comparing again, what do? We say 26 is left, so we compare 26 is less than 33, so there will not be any exchange that will happen, and I increment left by 1. So my left now reaches 20. As 20 is compared, so 20 is again less than 33. There will not be any exchange happening, and then we reach left plus plus, that is 18. So when I reach left plus plus and left is 18, 18 is again less than 33, and we observe that right remains at 41. Now as there is no exchange happening and again I do left plus plus, So my left reaches 41, that is, it becomes equal to right. And at this stage, the left and the right are going to interchange or exchange each other. So that is the place where my 33 will be placed, and I will swap the values of 33 and 18. So my left side of the list recursively after the divide and conquer quick sort application becomes 18, 26, 20, 33 and 41. You will observe that this is a recursive function which will be happening, and after the second iteration which is applied on the left side of the unsorted list, my 33 reaches a particular position, and then again recursively we keep applying the quick sort algorithm to sort the left list. Once the left list is completely sorted down, then we sort the right side of my list. Now let's see few advantages of using a quick sort. As we see, the quick sort recursively partitions the particular list, finds out the left part and the right part in my list, and then sorts the data at a particular order. And when I sort the data in a particular order, it runs it faster as it is dividing the list. If the size of my list is n, it automatically divides all the time my list into n by 2, as that is the basic strategy of divide and conquer algorithm. Now, it uses only a small auxiliary stack. That is, if you observe that when we sort the data in quick sort, it uses a small stack, that is a small memory, where my data is temporarily stored. It does not temporarily store much of a data, as it automatically exchanges the data and stores it immediately at its final position. The data is exchanged only when the pivot element is got a fixed position, and there is a slight swap of data which happens when we need to exchange the values of left and right. So the auxiliary stack that is used in quick sort is very small. So the space complexity of my quick sort is very low. It requires only n log n time to sort the n element, not that we don't have to compare the continuous memory locations, that is all the elements in the list need not be compared. So the time required for actually sorting the elements is n log n, as we keep on dividing the list into n by 2 partitions, and it has very small inner loop, which means that my inner loop only compares the left and the right element. There are no complex loops which will increase the time and the space complexity for my quick sort. Now let's see few disadvantages, as everything which comes with an advantage has few disadvantages also. Now what is disadvantage? It is recursive, as we've observed that quick sort always follows a recursive algorithm approach, because every time that I need to follow or I need to get a pivot element fixed at its location, I need to partition it. So if we try to implement this without recursion, then the implementation becomes extremely complicated. So quick sort has to be implemented using recursion and using the divide and conquer strategy. It requires n square time in the worst case scenario. Now what do you mean by the worst case scenario is, if I have chosen a pivot element which needs to be fixed at a location where the comparison takes a lot of time, then it becomes a very large time space complexity issue, as the time required for us to sort it even after using recursion is very large. It is fragile. Now what do I mean by the term fragile? If there is a very small error that happens during the comparison stage, then the whole small comparison leads us to a larger problem. That is, if I don't do a single calculation properly, my sorting technique fails. So That is the reason we say quick sort is a fragile algorithm. But with the space complexity, as it takes very less space on the auxiliary stack, it becomes a very easy and the suitable method to sort the element for the large number of lists. It helps us to sort it faster because all my lists are divided into n by 2 partitions. Thank you.